This is Elaine McCormick for Lab 9, Physics of Extreme Sports with Ropes 2. The purpose of this lab was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We looked at the 2D motion, which is the x and y components, and used the fundamental principles of the momentum principle and the energy principle to analyze the motion and predict a motion using a model. I'll discuss the final results at the end of the lab, but first let's look at my tracker data that was given by Dr. Greco. I set a calibration stick for the relaxed length of the spring, and then a fixed attachment point is where I put the origin. Then you run it, you can see I'm collecting data at a point mass, and I'm going to take this and put it into Excel. So here are my data points, and I'm going to use this this spring mass data in my Python code, which I'm going to run a model and a simulation. So first we're going to set up the model, which is going to be using this code. I'm going to insert the mass as well as the initial position I found from tracker, and then our spring constant we have from our previous lab as well as the relaxed length. And this is going to calculate with an orange ball and show how the motion runs. Then to compare it, I made a simulation of this type of motion using the data imported from tracker. And I put that up in here, which is going to show a blue ball, which is my tracker data. So let's first look at the X motion on our graphs when I run this code. So what you're going to see here is that as time increases, we're going to see the red and the green, which the green is in connection to the model, and then the red is the simulation. And so this is our X motion, and I'm going to use this later to analyze the period for X component. Now let's look at the Y. So I'm just going to change this here in my code to compare the two balls as they run in the Y component. So as it runs, same deal. You can see the green in the Y. Green again is the model, red is the simulation. Alright, so what we're going to do with all this data. Back to my PowerPoint. What does it mean? Compare the period of oscillation you found from the X component with the one you found from the Y component. So as I stated, finding the period, you go from trough to trough. So for the model, I found it to be 1.492 seconds, and for the simulation, I found it to be 1.482 seconds. And the difference is about 0.01 seconds. Then for the X component, the model is 1.674 seconds, and the simulation is 1.625 seconds. The difference is about 0.049 seconds. It's a little bigger for this one, but they're both relatively small. Why are these different? It's because when we look at the actual data from tracker, you're going to take into account some air resistance and little forces because it's a real-life example, whereas the simulation only accounts for gravity and the spring force, making them slightly different when we looked them up. Okay, or calculated them. Next question. With the new choice of system, determine the work done by the surroundings. Is the energy principle satisfied? So, what our system is now going to be is the Earth plus the spring plus the ball. And then our surroundings are space or nothing. Therefore, the contributing work done by the surroundings is none. So the change in energy is going to be equal to 0 because it's all internal. Any change is within the system. So this satisfies the energy principle because the change in energy is 0 and all the energy remains in the system. It just changes form. So finally, we're going to look at the last question here, which is asking us about the gravitational potential energy in our model if we change the location of the origin from 0 to the distance L plus mg over k below the attachment point. So how does this change the physics of the system? And discuss what effect this had on my plots. So what we're going to look at here is we're really just changing the location of the origin. So the sum of all the energies will be less for the origin than the sum of all the energies at the new origin's original location. So the new one is less than the old one. And this is because potential energy has to do with interacting objects. So you get different values based on the origin choice because it changes based on distance. but the physics of the system doesn't change because the changes in energy are all going to be the same. Therefore, the change in energy stays the same and the object behaves the same, and all my graphs will behave the same. Finally, our main result for this lab is that our lab agrees with the energy principle, Newton's second law, and conservation of energy is equal to the work done by the surroundings. And so when we include the Earth, the ball, and the spring in our system, delta E is equal to 0 for all of our test cases. Therefore, changing the origin does not change the physics.